It feels as though nearly every day yields another extraordinary finding from somewhere in the cosmos. The rate at which astronomers are discovering new planets and even entire solar systems is so high that simply staying current with these advances has become a challenge. The news is constantly reporting on newly found worlds, revealing novel properties of our universe and showing us just how much capacity it has to surprise us. However, I want to take this feeling of wonder and elevate it even further. To achieve this, I invite you to contemplate the living organisms that could be our cosmic neighbors, not just within our own galaxy, but across the entire universe. Consider the possibility that, far beyond ourselves and the flora and fauna we know, there are undiscovered life forms on the countless worlds we are only now beginning to find. To start this journey, I suggest we engage in a little bit of mathematics. You see, within our galaxy, planets actually outnumber the stars. This isn't all that surprising when you realize the Milky Way is home to approximately 300 billion stars. That's 300 billion, a truly immense figure. Even our own star, the Sun, is orbited by over 100 planets, moons, and significant asteroids. Each of these celestial bodies possesses its own distinct characteristics, and a great many of them might have the potential to support life. If this arrangement is typical for other stars throughout our galaxy, then a staggering 30 trillion such objects should exist. Figures of this magnitude are typically confined to the realm of astronomy, or perhaps the calculation of a nation's debt. Out of those 30 trillion theoretical worlds, humanity has identified fewer than 4,000 so far, which amounts to an infinitesimally small portion of the whole. And yet, the diversity of worlds we've observed even within this tiny sample is absolutely breathtaking. We have found planets that orbit inside their star's atmosphere, worlds entirely submerged in water, and solitary planets roaming through the cold darkness of space, unbound to any star. These discoveries only make one wonder what other incredible worlds await us as our observational tools grow ever more powerful and precise. Yet, the sheer scale of these numbers also points toward a more intriguing conclusion. I want you to try and envision a world as alien as your mind can conjure, a planet unlike any we have ever documented. Perhaps it has an unusually high concentration of a rare element like terbium, or maybe it's the moon of a rogue planet, drifting in perpetual cosmic night. Or you could picture a world much like Earth, with life thriving on land and in the oceans, but with a fundamentally different chemical basis. Go even further, and imagine something truly unbelievable, like a planet with an average density less than that of water, or one forged from pure iron. Let's assume the chance of such a world existing is just 1 in a million, similar to your odds of being struck by lightning in any given year. Even with such a remote probability, you can be certain our galaxy alone hosts about 10 million such planets. If you decrease those odds to just 1 in a trillion, our galaxy would still contain roughly 10,000 of these worlds. Ultimately, no matter how peculiar the world you imagine is, provided it adheres to the basic laws of physics and chemistry, there's a strong likelihood that a very similar planet exists somewhere in the Milky Way. And if that doesn't capture your imagination, remember that our universe contains billions of other galaxies, each probably holding a similar census of planets. So, what does this imply about life itself? The incredible variety of planets strongly suggests that we should anticipate an equal, if not greater, diversity among living organisms. This, however, brings us to a significant hurdle. We are only acquainted with a single version of life, our own, which is predicated on the chemistry of carbon-based molecules and depends on liquid water. The entirety of Earth's biological richness stems from one isolated experiment in one of the universe's innumerable cosmic laboratories. Consequently, our home world and the life it nurtures offer very little guidance when we attempt to establish benchmarks for the unimaginable variety life could take across the galaxy. Despite this, the limited understanding we have of life on Earth is our only starting point, so we must use it as extensively as we can. Our investigation into the theoretical forms of life in the galaxy will start by setting what I call the rules of the game, the core principles that have sculpted life here into its current form. I contend that the most fundamental of these principles, evolution by natural selection, is likely to be operational under nearly any set of conditions, anywhere in the cosmos. The second major principle, that life is based on carbon chemistry, is probably not as widespread. Nevertheless, it's far easier to work from a foundation of familiarity, so when we explore life, our focus will remain primarily on variations of the carbon-based chemistry we know. In this exploration, I will separate all conceivable life forms into three distinct groups: life that is similar to ours, life that is dissimilar to ours, and life that is profoundly different from ours. For fairly clear reasons, our most immediate and detailed focus will be on the first of these categories. Once we've laid out the fundamental rules for assessing the probability of life like ours appearing and surviving, we will then explore the potential outcomes of these rules across the varied environments of our theoretical exoplanets. In this exploration, I will separate all conceivable life forms into three distinct groups: life that is similar to ours, life that is dissimilar to ours, and life that is profoundly different from ours. For fairly clear reasons, our most immediate and detailed focus will be on the first of these categories. Once we've laid out the fundamental rules for assessing the probability of life like ours appearing and surviving, we will then explore the potential outcomes of these rules across the varied environments of our theoretical exoplanets. Let's start with a planet in the habitable zone, which is defined as a terrestrial world orbiting its star at a distance that permits liquid water to remain stable on its surface for long stretches of time. Evaluating the conditions on such a planet is our most straightforward task, as we have already extensively studied one such world, our own Earth. A great number of recently found exoplanets exist within the habitable zone, a region where liquid water could potentially endure on their surfaces for extended periods. This includes the planet orbiting Proxima Centauri, the nearest star to our Sun, and 3 of the 7 worlds in the TRAPPIST-1 system. However, a planet might harbor a subsurface ocean, where vast bodies of liquid water are situated between a solid rock crust and a thick overhead layer of ice. Such worlds are not merely theoretical. They exist right here in our own solar system, with subsurface oceans confirmed on Pluto and several moons of the outer planets. Even rogue planets, which have been ejected from their home systems to wander through interstellar space, are not necessarily cold, lifeless husks. They can possess internal heat sources, much like other planets, and this warmth is completely independent of the presence of starlight. Consider also a water world, a planet entirely without land. The defining characteristic of such a place would be the distinct layers of water at different depths of its global ocean. While on Earth these layers are formed by temperature and salinity, on an exoplanet, immense pressure could be the critical factor, potentially allowing for different forms of life to evolve in each distinct layer. Then there are planets in synchronous rotation, which always present the same face to their parent star, just as our moon always shows the same side to Earth. It's likely that many of the worlds you've heard about, such as those in the TRAPPIST-1 system, fall into this category. A key attribute of these planets is an extreme environment where one hemisphere is scorchingly hot and the other is perpetually dark and frozen. Life here could only emerge within the narrow transitional zone between the fire and the ice, a region battered by ferocious winds that constantly transfer heat from the star-facing side to the cold one. Another fascinating possibility is the super-Earth, a rocky planet with a size somewhere between that of Earth and Neptune. These worlds seem to be incredibly common throughout the universe, and our own solar system might be unusual for not having one. Because of their significant mass, the defining feature of these planets is their tremendous gravity. While creatures living deep within their oceans would be untroubled by this, any life that ventured onto land would need to develop specialized strategies to manage the immense gravitational pull. Life on our planet has evolved numerous solutions to cope with more moderate gravity, from the capillary systems in plants to the exoskeletons of insects and the internal skeletons of mammals. But what adaptations might arise if Earth's gravity were twice, or even 10 times, stronger? If reptiles on such a world evolved a swim bladder similar to a fish's to adapt to the crushing gravity, could they ultimately become flying dragons, soaring through the dense atmosphere? By exploring possibilities like these, you and I can start to move beyond our fixed, conventional ideas about the world and begin to envision life that is completely unlike our own. We will undertake this journey step by step, systematically letting go of the familiar traits of life that we have long considered essential. What if we entertain the idea of life that isn't based on carbon, but on another element entirely? Silicon, for instance, is positioned directly below carbon in the periodic table and shares many of its properties. This similarity is why silicon-based life has been a staple of science fiction for decades, with one of the most memorable examples being a 1967 episode of Star Trek. In it, miners on a faraway planet encounter the Horta, which are rock-dwelling, silicon-based beings that are at first hostile to humans. We will delve into the kinds of planets where such creatures might originate, but this exploration also raises more profound questions. If you were to encounter such beings, would you even recognize them as life? Is it possible that we would perceive a silicon-based life form not as a living creature, but simply as an inanimate rock? The further we stray from the familiar forms of life we know, the more challenging it becomes to provide definitive answers to such questions. Life could be founded on elements that are scarce on Earth but plentiful in other cosmic environments. Scientists have recently supported this very idea, publishing research that catalogs the diverse chemical compounds present in other stars, and by extension, likely in the planets that orbit them. If you truly let your imagination roam free, you can conceive of all manner of life forms that are utterly alien to us. Perhaps life that isn't based on chemistry at all, or doesn't adhere to the laws of natural selection. Ultimately, the central question I am trying to answer can be summarized this way. Given the incredible complexity and variety of exoplanets, both discovered and imagined, will we discover a corresponding complexity and diversity among the living things on these worlds? Our entire investigation into the possible emergence of life elsewhere in the galaxy is made possible by two overarching principles, which also set the boundaries for such an inquiry. The first principle is that the physical universe operates according to a relatively small set of universal laws. The second is that the physical laws we observe on Earth today are applicable at every location in the universe and throughout all of time. These two concepts are fundamental to the thinking of every scientist and have been a core part of my own education from the very beginning. In fact, these ideas are what anthropologists might term basic beliefs, convictions so integral to a group that they are simply taken for granted and shared without question. However, I have come to realize that these two foundational beliefs are not widely understood by the general public, let alone accepted as axiomatic truths. This gap in understanding is something we must address as we explore the vast possibilities that the universe holds for life in all its potential forms. The issue isn't that most people doubt certain scientific principles. It's that when you contemplate vast questions like the possibility of extraterrestrial life, these foundational ideas often don't come to mind. That's why I believe it's essential for us to explore these core concepts, which is precisely the goal of this chapter. We will begin with the fundamental laws of physics and chemistry that will act as our guideposts as we consider what hypothetical life beyond Earth might be like. Let's start with the rules that govern the familiar world you see every day, the one populated by normal-sized objects moving at ordinary speeds. This domain of science is known as classical physics, and you can visualize it as three massive pillars supporting our entire understanding of the physical world. It's crucial for us to examine these laws before we venture into more abstract scientific territory. The first of these pillars is mechanics, the system of laws first articulated by the English scientist Isaac Newton to explain our daily physical experience. This branch of science, which describes how material objects move, has fascinated physicists for ages. Although thinkers dating back to ancient Greece attempted to fully explain motion, they had limited success until Newton developed a revolutionary mathematical tool, what we now call differential and integral calculus, to finally derive the laws governing projectiles. The principles Newton devised, which we refer to as Newton's laws of motion, are remarkably straightforward. The first law states that an object will maintain its state of motion or rest unless compelled to change by an external force. The second explains that an object's acceleration is directly proportional to the force acting on it, and inversely proportional to its mass. Finally, the third law posits that for every action, there is an equal and opposite reaction. These rules apply universally to any object in motion, anywhere in the cosmos, a concept we will revisit. In short, the first law gives you a way to recognize when a force is at play, and the second describes the result of that force's influence. By themselves, however, these laws only describe how forces affect movement. They don't reveal what specific forces actually exist in nature, which leads us to the forces that manage the behavior of planets. Perhaps Newton's most famous contribution to science is the law of universal gravitation. This principle holds that any two objects in the universe attract each other with a force, gravity, that is directly related to the product of their masses and inversely related to the square of the distance separating them. To put it simply, if you double the mass of one object, the gravitational force between them also doubles. Conversely, if you double the distance between them, the force of attraction weakens by a factor of 4. It's a surprisingly simple concept, yet Newton could never have guessed that his laws would one day enable us to calculate the masses of planets orbiting stars trillions of miles away. For instance, as we'll explore in Chapter 5, A highly effective method for finding exoplanets is to observe the slight dimming of a star as a planet passes between it and us, an event called a transit. By measuring the interval between these transits, we can apply Newton's laws to determine the planet's distance from its star. By combining that orbital data with the star's known surface temperature, we can begin to answer profound questions, such as whether liquid water could exist on that planet's surface. From there, we can start to speculate about the potential for life in other star systems, an application Newton's contemporaries could never have imagined. The significance of his universal view, however, extends far beyond the practical search for exoplanets. In fact, one could argue that the entire foundation of modern science was built upon the emergence and evolution of Newtonian mechanics. It established the very scope of scientific possibility, from making theoretical predictions about undiscovered phenomena to testing those predictions against the harsh realities of the physical world. In a way, every technological marvel of our civilization is a direct result of Newton's method for investigating nature. We can take this concept even further. The Newtonian picture of the solar system is akin to an intricate clockwork mechanism, where the planets move with the same predictable regularity as a clock's hands, governed by the same laws that ensure a clock's gears turn smoothly. If you expand this model to the entire universe, you are left with an orderly, consistent, and foreseeable reality. A cosmos where surprises and unforeseen turns of fate are simply not possible. Even the fantastical flying dragons mentioned in the last chapter would have to adhere to Newton's laws. To stay airborne, the buoyant force from their specialized swim bladders would need to overcome the planet's gravity, while their flight control would depend on the interplay between the lift from their wings and their own mass. This worldview of the cosmos as a precision machine eventually spread far beyond the natural sciences. Some scholars even contend that the United States Constitution is indebted to Isaac Newton. Their reasoning suggests that the Founding Fathers, seeing that Newton could uncover the laws that govern the entire universe, believed they too could discern and formulate the principles upon which to construct an ideal society. As we are about to discover, the 20th century would deliver a powerful blow to the idea of an orderly and predictable nature. Before scientists began to reluctantly part with that concept, however, two major new scientific fields were established, both founded on the vision of the universe as an intricate clockwork machine. These are the other two pillars that will support our discussion of life on exoplanets: electricity and magnetism. Both of these forces have been recognized since ancient times. You are familiar with static electricity, the principle that causes wool socks to cling to towels after they come out of the dryer, and magnetism, the force that holds magnets to your refrigerator door. The ancient Greeks viewed electricity as a fascinating natural curiosity, and were even aware that electric charge exists in two forms, which we now identify as positive and negative. They observed that opposite charges attract each other, while similar charges push each other away. For centuries, human knowledge about electricity hardly advanced beyond these basic observations, and no practical applications for static electricity were ever devised. Magnetism, however, was a different story entirely. People soon found naturally occurring magnets in the form of iron oxide, more commonly known as magnetite or lodestone. Its discovery is shrouded in legend, with one tale telling of a Greek shepherd named Magnus, who found that the nails in his sandals were drawn to fragments of the stone, from which the term magnetism supposedly originated. Another legend speaks of an island in the Aegean Sea made entirely of magnetite, which would pull the iron nails from any ship that sailed too close, causing it to fall apart. Fables aside, these natural magnets possessed a single, profoundly useful quality. Pieces of lodestone would consistently align themselves with the North and South poles. This property made them invaluable as the first compasses, a tool that enabled people to navigate through completely unknown territories and became essential for sailors at sea and caravans in the desert. The Chinese were using simple lodestone compasses as early as the 1st century before the Common Era. Much later, during the 9th and 10th centuries of our era, Viking raiders from Scandinavia also relied on these compasses to find their way across the ocean or through dense fog. Further investigations into electricity and magnetism brought two crucial properties to light. William Gilbert, an English scientist and court physician to Queen Elizabeth I, established the fundamental law of magnets, that their poles attract each other can never be isolated, as every magnet inherently possesses both a north and a south pole. Then, nearly a decade after Isaac Newton's death, the French scientist Charles-Augustin de Coulomb meticulously measured the force between electric charges. He determined that it could be described by a straightforward equation that bore a strong resemblance to Newton's law of universal gravitation. Since we will not need to use his equation in our later discussions, I will not detail it here. This was the state of human understanding as the Industrial Revolution began, with most people perceiving static electricity and magnetism as entirely unrelated phenomena. The conceptual wall separating these two forces started to crumble during a physics lecture in Copenhagen, thanks to a new technological advance. The Italian scientist Alessandro Volta had invented a device he named the electric pile, which we recognize today as the battery. It was capable of producing a flow of moving electric charges, an electric current, which was a novel and previously unknown manifestation of electricity. It was this new invention that would unlock a far deeper understanding of both forces. During a demonstration of Volta's battery to his students, the lecturer, Danish physicist Hans Christian Ørsted, noticed that the needle of a nearby compass deflected every time the device generated a current. This was the first proof that moving electric charges create magnetic effects, establishing a clear link between electricity and magnetism. You have almost certainly used the technological descendants of Ørsted's discovery multiple times today without giving it a second thought, as his observation led directly to the invention of the electric motor. Decades later, the English physicist Michael Faraday supplied the final piece of the puzzle. He showed that changing the magnetic field in the vicinity of a wire, for instance by moving a magnet through a copper loop, causes an electric current to flow through that wire, even when it is not attached to any power source. This discovery, known as electromagnetic induction, completed the unified picture of these two fundamental forces. We can therefore summarize our knowledge of electricity and magnetism with four essential principles. First, opposite electric charges attract, while like charges repel, which is Coulomb's law. Second, magnetic poles are never found in isolation. Third, moving electric charges are the source of magnetic fields. And fourth, a changing magnetic field will always produce an electric current. These four ideas, when expressed mathematically, serve the same role for electromagnetism that Newton's laws do for mechanics, offering a complete description of everything we understand about these phenomena. With this foundation, we again find ourselves in a position where a few simple, elegant laws can explain a vast array of complex natural events. We will need to draw on these principles frequently as we explore the potential for life on exoplanets. In Chapter 13, for example, I will explain how coronal mass ejections from stars, immense clouds of ionized gas governed by electromagnetism, can impact a planet's biosphere and possess the power to devastate even an advanced technological civilization like our own in a matter of hours. We'll also examine how a world like Mars, which lacks the protective magnetic field found on Earth, is left vulnerable to solar radiation that could easily erase any signs of life on its surface. The principles of electricity and magnetism become particularly crucial as we explore the potential for life forms completely different from our own. These fundamental interactions not only allow us to characterize the complexity of life as governed by chemistry, but more importantly, they provide the most powerful tools we have for guiding our search for life across the cosmos, by helping us understand the natural constraints on its emergence and evolution on other worlds. The physical laws I'm referring to are collectively known as Maxwell's equations, named for the Scottish physicist James Clerk Maxwell. While he didn't discover these laws individually, his unique genius was in recognizing they constituted a unified, coherent mathematical system. Maxwell was among the foremost mathematicians of his era, specializing in advanced fields we now call partial differential equations and vector calculus, and it was this expertise that allowed him to bring the concepts of electricity and magnetism together. When Maxwell applied these advanced mathematical tools to the four established laws of electromagnetism, he uncovered a result that was nothing short of breathtaking. His equations predicted that accelerating electric charges must produce waves composed of oscillating electric and magnetic fields. Furthermore, these waves would travel through space at a velocity determined by the known forces between electric charges and magnets. Upon calculating this speed, Maxwell must have been astounded to find it was approximately 300,000 kilometers per second, the precise speed of light, revealing that light itself is a form of electromagnetic radiation. This discovery means that phenomena as diverse as a sock clinging to a towel due to static, a magnet pinning a list to your refrigerator, and even your ability to read these words are all connected manifestations of the same underlying physics. But the implications didn't stop there. Maxwell's equations suggested that visible light, with wavelengths spanning about 4,000 to 8,000 atoms, was just one small part of a much larger spectrum of electromagnetic radiation, with other wavelengths waiting to be found. Indeed, during the late 19th century, scientists confirmed his prediction by discovering this entire spectrum. First, they identified radio waves, followed by other bands with wavelengths longer than visible light, such as microwaves and infrared radiation. They also found radiation with shorter wavelengths, including ultraviolet rays, X-rays, and gamma rays. It was also determined that as the wavelength shortens, the energy of the wave increases, meaning if you stretch a wave of visible light, you get a radio wave, and if you compress it, you get an X-ray. Electromagnetic waves represent the vast majority of the data we can gather about exoplanets, traveling to us across interstellar space at the speed of light. Each part of the spectrum illuminates different cosmic processes. For instance, X-rays point to incredibly high-energy events, while infrared radiation informs us about cooler phenomena. Because Earth's atmosphere absorbs most of these wavelengths, with the notable exceptions of visible light and radio waves, we rely heavily on instruments placed on orbiting satellites and large ground-based telescopes to gather the necessary scientific data. Therefore, the very electromagnetic radiation predicted by Maxwell's equations serves as our essential tool for investigating the conditions on distant exoplanets. This is a topic I will return to in Chapter 5, where we'll delve into the search for life beyond our own solar system. The last foundational pillar of classical science is thermodynamics, a term created by combining the Greek root thermo, for heat, with dynamics, the science of motion. As its name implies, thermodynamics is the study of how heat, and energy more generally, is transferred. Much like mechanics and electromagnetism, our understanding of this field can be distilled into a few fundamental laws. For our purposes, we will concentrate on two of them, the first and second laws of thermodynamics. The first law states that while different forms of energy can be converted into one another, the total amount of energy in an isolated system always remains constant. The second law establishes that within an isolated system, the measure of disorder, which we call entropy, can only increase or stay the same over time. It can never decrease. The first law is a cornerstone of modern physics, establishing that energy can neither be created nor destroyed, only transformed from one state to another. This concept makes it useful to think about the energy that powers life, whether on Earth or on an exoplanet, as a continuous flow. Here on our planet, this flow begins with energy from the sun, moves through the biosphere as it is used by living organisms, and is finally radiated away into space as infrared heat. Consequently, for every hypothetical example of alien life we consider in this book, a primary step will be to identify and analyze all the available energy sources. In most scenarios, the main source of energy will be the planet's host star. However, we must remain open to other possibilities, especially since we know of ecosystems on Earth, like those near deep-sea hydrothermal vents, that thrive completely independent of the sun, drawing on thermal and chemical energy from our planet's interior. It is highly probable that comparable structures can be found on exoplanets, a notion we will return to when we examine forms of life that bear no resemblance to our own. The second law of thermodynamics is of paramount importance, not only when we formulate a definition for life in Chapter 3, but also when we delve into life completely alien to us in Chapter 16. The essential takeaway is that every living system, no matter its makeup, must maintain a high degree of order, and the second law of thermodynamics deals precisely with this concept. Its most profound consequence is an unyielding rule. If you establish an ordered system somewhere, such as life itself, you must compensate by generating a greater amount of disorder elsewhere in the universe. In the classical Newtonian framework, the cosmos is governed by a set of 9 natural laws, 3 governing mechanics, 4 describing electricity and magnetism, and 2 laws of thermodynamics. This perspective suggests that everything occurring anywhere in the universe can be fully explained by a system of equations compact enough to be printed on a t-shirt. However, for all its elegance and appeal, this depiction of reality is ultimately an oversimplification, paving the way for what we now call new physics. Some people assert that the great discoveries of 20th century physics, namely relativity and quantum mechanics, proved the Newtonian worldview to be fundamentally false, a statement with which I strongly disagree. The Newtonian model of the universe is built on experiments with objects of ordinary size traveling at normal velocities. New physics simply expanded the boundaries of scientific knowledge far beyond those everyday limitations. Relativity, for example, applies to objects approaching the speed of light or possessing immense mass, while quantum mechanics describes phenomena at the atomic and subatomic levels. Yet, when you apply the principles of these modern fields to objects of conventional size moving at typical speeds, you arrive back at the familiar Newtonian laws. This is why engineers who design highways and railway bridges still rely on the study of Newtonian mechanics. These new scientific fields might, at most, append a couple of additional laws to the magnificent 9 we already have. Relativity, for instance, rests on the fundamental idea that the laws of nature remain the same in all frames of reference. While we will seldom touch upon this theory for the remainder of the book, it becomes crucial in the hunt for rogue planets, those worlds drifting alone through interstellar space, a topic we will explore in Chapter 11. Quantum mechanics, however, presents a very different picture. Within the atom, physical events happen in ways that are completely foreign to our daily experience, creating a realm where nothing is certain or continuous, and nearly everything is intertwined, influencing everything else. Even though scientists have yet to agree on a single interpretation of the findings from this bizarre field, we can rely on a few general principles to add to our list of universal laws. For our purposes, the most significant discoveries from quantum mechanics relate to how atoms absorb and emit light. Electrons are not like planets orbiting a star. They cannot exist in any random orbit around an atomic nucleus, but are confined to very specific, allowable positions. An atom releases electromagnetic radiation, which includes visible light, whenever an electron drops from a higher energy orbit to a lower one. Conversely, an atom takes in radiation when an electron jumps from an inner orbit to an outer one. The frequency of this radiation, which we perceive as color in visible light, is determined by the energy difference between the electrons' starting and ending orbits. Because the possible orbital positions are unique for the atoms of each chemical element, the spectrum of radiation an atom emits or absorbs acts as a distinct fingerprint. This principle is the foundation of an entire scientific discipline known as spectroscopy, which we will cover in Chapter 5. As we will see, this specific outcome of quantum mechanics gives us a remarkable tool for assessing the life-bearing potential of worlds around other stars. Our entire understanding of the cosmos, therefore, is rooted in the search for a small number of universal laws, much like the ones we've already discussed. The profound simplification of our worldview that began with Newton's laws fuels the hope that a similar consolidation will happen as we deepen our knowledge of new frontiers in physics. This aspiration is what motivates modern physicists in their quest to develop what is sometimes whimsically called the theory of everything, a single equation from which all known and future principles could be derived. As its name suggests, such a theory would offer a complete explanation for everything. Of course, we remain a long way from achieving such a theory, and many respected scientists are skeptical that one even exists. Furthermore, it isn't necessary for our search for extraterrestrial life. Nevertheless, it's fascinating to contemplate the kinds of future technologies that might emerge from the insights of a theory of everything. Another overarching principle that will steer our investigation into alien life is the Copernican principle, named after the Polish astronomer Nicolaus Copernicus. He famously developed a mathematical model of the solar system that placed the sun, not the Earth, at its center, taking the first step on a long journey to the now obvious realization that our homeworld is not special. It is merely one rocky planet orbiting a typical star in an ordinary part of a common galaxy, among billions of other galaxies in the cosmos we can observe. There is a profound gift in accepting that our planet is not unique, as it suggests that the natural laws we uncover in our time and place are constant across all of space and time. This modern viewpoint stands in stark contrast to that of the ancient Greeks, who were trailblazers on humanity's journey toward science but saw the cosmos very differently. Their cosmology placed Earth at the very core of creation, granting it a privileged status separate from everything else in existence. On Earth, they believed all matter consisted of 4 fundamental elements: earth, air, fire, and water, while the heavens were thought to be composed of a completely different 5th element, known as ether or quintessence. Under this model, the celestial realm was considered a domain of absolute perfection, where planets and stars were carried on flawless spheres in roughly circular orbits. This entire, meticulously built Aristotelian cosmology was directly challenged by the lunar craters and sunspots Galileo observed through his telescope. Effectively, the ancient Greeks operated with 2 distinct sets of natural laws, one governing our terrestrial world, and a separate one for the heavens. It was none other than our familiar figure, Isaac Newton, who dismantled this 2-tiered view of the universe. As the well-known story goes, Newton was in his family's garden one day when he witnessed an apple drop from a tree while simultaneously noticing the moon in the sky. He understood that the apple fell because of Earth's gravity, a force that Galileo and others had already studied, and he was also aware that the moon follows a curved orbit around our planet, instead of traveling in a straight line. Applying his first law of motion, he concluded that some force must be constantly acting on the moon to maintain its orbit. Without it, the moon would simply drift off into deep space. This led him to ask a question that feels elementary to us now, but was a stroke of genius at the time. What if the very same force pulling the apple to the ground is also the one holding the moon in its celestial path? The answer, as we now know, is a definitive yes. We now fully grasp that the force Newton identified is what we call the law of universal gravitation, which means there is fundamentally no distinction between the gravitational pull of objects on Earth and that of bodies in space. His breakthrough provided the first concrete piece of evidence for what is known as the Copernican principle, the concept that the laws of physics and chemistry here on Earth are universal. Since the 15th century, a massive body of evidence has been gathered that continues to validate this principle. For instance, if you compare the light signature of a particular atom in a lab on Earth to the light from an identical atom in a far-off corner of our galaxy, or even another galaxy, the patterns are precisely the same. Similarly, when we witness the decay of radioactive elements during supernova events in galaxies billions of light-years from us, and check it against the decay of those same elements in our labs, the results match perfectly. All this information points to an unavoidable conclusion. Our planet is not unique, and its physical laws are the same ones that govern the rest of the cosmos. Furthermore, when you observe a galaxy that is 1 billion light-years distant, the light reaching your eyes actually began its journey 1 billion years ago, which means you are essentially looking back in time. And the overwhelming evidence confirms that an atom from 1 billion years ago in that distant galaxy behaves no differently than its modern counterpart in a laboratory today. The rules of physics and chemistry are not only constant across space, but have also remained unchanged for billions of years. As I touched on in the last chapter, our knowledge about the conditions on exoplanets is already quite substantial, and we can be certain that the fundamental laws we've reviewed are just as valid on these worlds as they are here. This understanding allows us to infer certain characteristics of potential life forms on those planets, but it also places firm limits on what we can realistically imagine. For example, the flying dragon I proposed earlier is entirely possible because it doesn't defy Newton's laws of motion. Its strange appearance is irrelevant. What matters is that only life forms conforming to the known laws of science are actually possible. So, with this crucial framework established, let's turn our attention to the specific laws that govern living systems themselves. Chapter 3. Life. What exactly is it? You and I both feel we have a solid, intuitive grasp of what life is, and we're sure we'd recognize it on sight. Yet, providing a precise explanation for it has proven to be an exceptionally tricky task. So, what are the definitive characteristics of the phenomenon we refer to as life? The central challenge lies in the fact that life on Earth, which is our only known example, presents an incredible spectrum of complexity and variety. There is also a profound gap separating living things from inanimate matter, and a successful definition of life has to bridge and clarify this distinction. It's understandable, then, that attempts to define and explain life stretch far back into our history. Aristotle, for instance, proposed that every living being is composed of a physical body and a non-physical essence he called a soul. This concept eventually developed into the theory of vitalism, which held that a special, non-material, vital force is what separates the living from the non-living. This belief was ultimately disproven with the rise of cellular and molecular biology in the 19th and 20th centuries. We now recognize that, at the molecular scale, living organisms abide by the very same chemical laws that govern the entire universe. The key difference is their vastly greater complexity. Even with this knowledge, the sheer variety of organisms on our planet makes formulating a single, simple definition of life an exceedingly difficult endeavor. A great many contemporary scientists have concluded that devising a simple, all-encompassing definition of life is likely an impossible task. For our discussion, it is enough to understand that there are three dominant frameworks for tackling this question. Those that rely on listing life's properties, those that frame life as a continuous process, and those that derive a definition from the principles of thermodynamics. We will explore each of these categories individually. Those who favor the first approach attempt to define life by assembling a list of attributes that are intrinsic to living things. Under this framework, any entity that displays all, or at least a majority of these characteristics is classified as alive. Conversely, anything that lacks most of these essential qualities is considered non-living. A standard list, which you might find in any conventional biology textbook, will typically outline several required properties and capabilities. This classic checklist specifies that a living system must demonstrate several key functions. These include adaptability, or the capacity to adjust to long-term changes in its environment, growth and development over its lifespan, and self-regulation, which is the ability to maintain a stable internal state, like body temperature. The list also mandates metabolism for processing outside resources, a structure built from one or more cells, the ability to reproduce, and finally, irritability, or a responsiveness to immediate changes in its surroundings. The fundamental issue with compiling such lists is that as soon as you establish a seemingly complete set of criteria, you inevitably discover organisms that are undeniably alive yet fail to meet one or more of them. A mule, for example, is the living offspring of a horse and a donkey, but it is sterile and cannot reproduce. Physicist Daniel Koshland offered an even more insightful example. A single rabbit, by itself, cannot reproduce and would therefore fail the test, whereas two rabbits together can, which suggests the pair is collectively alive and complicates the very notion of reproduction as a simple checkbox.
One potential solution is to propose that an entity is alive if it fulfills most of the criteria, even without meeting every single one, which is essentially adopting a legal principle known as the preponderance of evidence. Yet this tactic immediately introduces a fresh dilemma. You are then forced to make a judgment call about which characteristics on the list are negotiable and which are absolutely essential. A powerful illustration of the difficulties you face with this principle comes from the search for life on Mars. When the Viking landers arrived on the red planet's surface in 1976, hopes were incredibly high for finding life. The mission's design incorporated at least 4 experiments intended to identify the chemical residues of an Earth-like metabolism in the Martian soil, meaning the entire program's logic was built upon a definition of life reduced to this single attribute. Almost as soon as the landers began sending back data, many researchers acknowledged that the experiments could produce false positives from clearly non-living sources, such as specific chemical reactions occurring in the Martian regolith. It is now widely argued that the decades of debate over the Viking mission's results are, in large part, a direct consequence of the narrowly conceived definition of life that was used to design its experiments in the first place. The shortcomings of the checklist approach are perfectly captured in an episode of Star Trek: The Next Generation, where the android, Data, makes a case for fire being a living entity. His argument is surprisingly strong. Fire consumes fuel from its surroundings, processes it, and expels waste products. Furthermore, it is capable of growth, reproduction, and responding to environmental shifts. By these measures, fire meets nearly all the criteria on our list, perhaps with the exception of self-regulation, yet almost no one is prepared to classify it as being alive. The developing science of ecology presents another way you can use lists to conceptualize life. Rather than concentrating on the attributes of an individual, an ecologist considers how that organism integrates into the intricate web of relationships within its broader ecosystem. The most prominent example of this viewpoint is likely the Gaia hypothesis, which was put forth by ecologist James Lovelock, who conceptualizes the entire Earth, including both its living and non-living elements, as a single, massive organism. This hypothesis often leads to the suggestion that our planet's diverse ecosystems work in concert to maintain a stable environment that is favorable for life's continuation, a concept named for the ancient Greek goddess who was the mother of all living things. However, the Gaia hypothesis has faced considerable criticism, primarily because Earth's actual geological record is filled with catastrophic events that do not align with the image of a planet governed by a careful and systematic ecological balance. For instance, our planet has endured periods where it was a giant snowball, its surface and oceans completely frozen over and covered in ice, a state that could only be broken by the immense power of volcanic eruptions. Consequently, while it is true that all organisms on our world are part of vast ecosystems, the ecological perspective ultimately just adds one more requirement to our list. Being part of a large ecosystem is necessary for life. But this property, much like the requirement for a cellular structure, may hold true for Earth, but offers no guarantee of being a universal necessity for life on exoplanets. Even though you might be conditioned to think of life in the cellular terms we are familiar with, there's no compelling reason to believe that life on exoplanets must conform to this model. Essentially, while the characteristics I've previously outlined are true for Earth's organisms, it is far from certain that extraterrestrial life would be bound by the same properties. Consequently, as we prepare to venture into the galaxy,
It's wise to carry our checklist, but remain aware that its utility in identifying alien life may be quite limited. Back in 1994, NASA renewed its commitment to searching for cosmic life and convened a panel of leading scientists to establish a working definition for the concept. At the prompting of Cornell astrophysicist Carl Sagan, the group settled on defining life as a self-sustaining chemical system capable of Darwinian evolution, a phrasing that has since become known as the NASA definition. Although this formulation is unapologetically centered on our own planet's biology, we will discover its significant value as we speculate about potential life forms on exoplanets. The mechanism of Darwinian evolution is more commonly referred to as natural selection, a process I contend is likely active on a vast number of exoplanets. On Earth, its operation is straightforward. Every organism inherits genetic material from its parents that shapes its traits. These characteristics are pivotal in determining whether the organism survives long enough to pass that genetic code to the next generation, a principle you may know as survival of the fittest. Over many generations, traits that enhance survival tend to build up within a population, which is how natural selection produces organisms that are exquisitely adapted to their specific environments and gives rise to the incredible biodiversity you see on our world. It is crucial to note, however, that while every known living thing on Earth is a result of natural selection, this doesn't automatically disqualify something not created by this process from being considered alive. We will delve into several such possibilities in Chapter 16, where we explore life profoundly different from our own. The NASA definition is fundamentally one of several efforts to define life by the process that brings it into being. The core idea is that to know if something is living, you must first understand its origins. According to this viewpoint, if an organism is the product of natural selection, then it qualifies as alive, which effectively makes the evolutionary process itself the benchmark for what constitutes life. Of course, other processes have been suggested as the foundation for defining life, with one of the most compelling ideas emerging from systems theory and the concept of emergence. This perspective frames life as an emergent property that arises from sufficiently complex chemical systems. To grasp emergence, consider the simple analogy of a sand pile you build one grain at a time. As the pile grows, the web of forces between the grains becomes ever more intricate, all stemming from simple points of contact. At a certain point, perhaps with the millionth grain of sand you add, a new phenomenon occurs. A sudden avalanche cascades down one of the slopes. This avalanche is an emergent property of the entire collection of sand grains, because a single grain of sand cannot produce 1/10,000th of an avalanche. To get the cascade started, you must first assemble the full collection of a million grains, which has led proponents of this idea to argue that life is a kind of chemical avalanche that emerges when a system achieves a critical level of complexity. The principal weakness of this category of definitions is that they require an exceptionally detailed and exact understanding of how a particular system arrived at its present condition. In Chapter 5, I will address the even greater difficulties that await you in detecting signs of life on other worlds, let alone deducing how that life might have evolved. Even on Mars, where we can deploy landers and probes to perform in situ, a Latin term meaning on-site, measurements, obtaining conclusive evidence of past or present life has proven to be an immense challenge. So you can imagine how much harder it is to both find life and trace its history on a distant exoplanet. When physicists approach a puzzle, such as defining life, their core method is to identify the most fundamental laws of nature that govern the system they are examining. This technique has been a cornerstone of science at least since Isaac Newton showed that the motion of any object in the universe can be described by the three laws he devised. As I mentioned in the last chapter, one might even say the ultimate goal of physics is to boil down the universe's operating manual into a set of equations compact enough to fit on a t-shirt. Therefore, when a physicist considers life on Earth, they immediately focus on two essential parameters: energy and entropy. These concepts are the bedrock of thermodynamics, a branch of science that was developed and refined in the 19th century. As you may recall, we previously touched upon the first and second laws of thermodynamics, which can be summarized simply. The first law states that energy can be converted between many forms, but can never be created or destroyed. The second law dictates that, in an isolated system, the degree of disorder, known as entropy, can only increase or stay the same over time. It can never decrease. A common way to visualize these laws is to think about a teenager's bedroom, a system often demonstrating a natural tendency toward increasing disorder. Over time, any room tends to become progressively disordered. Its level of chaos increases, which is another way of saying it moves toward a state of greater entropy. You can picture this clutter as the system's natural default condition. The only way to prevent this disarray, and thus hold the system far from its equilibrium, is through constant cleaning. This activity demands energy, which for a teenager is typically derived from food, or, more accurately, from food provided by their parents. In accordance with the first law of thermodynamics, this energy cannot just vanish. It is eventually released into space as heat. Consequently, to preserve a condition of high order, or low entropy, a continuous stream of energy must pass through the system. In the vocabulary of physics, this energy flow is what maintains the system in a highly organized state, distant from its natural equilibrium. A living organism, such as your own body, is an excellent example of such a highly ordered system, much like an immaculately kept bedroom. If left on their own, the atoms comprising your body would rapidly devolve into an unstructured heap of matter, not unlike that messy room. The energy that flows into your body from the meals you consume, energy that originally comes from the sun, is what keeps you far from this state of equilibrium, preventing your body from becoming just a disordered pile of atoms. Taking all this into account, we can describe a living system as one that is sustained in a state far from equilibrium by an influx of energy. This, however, is less a formal definition of life, and more a crucial characteristic of it, a property that could signal life's potential existence. From a logical standpoint, this property is a necessary condition for life, but it is not a sufficient one. To put it differently, while every living thing requires an energy flow to sustain its high degree of organization, not every system that exhibits this property is actually alive. A growing snowflake, for instance, is a beautifully ordered system that harnesses thermal energy for its formation. Yet no one would argue that it is a living entity. This thermodynamic perspective on life will become especially important in Chapter 16, where we explore the possibility of life forms completely different from our own. Let's consider a note on technology. Back in 1960, during excavations in Tanzania's Olduvai Gorge, paleontologists Lewis and Mary Leakey unearthed the fossilized remains of a hominin alongside fragments of stone tools. This hominin, who would later be named Homo habilis, meaning handyman, was the first of our distant ancestors to use materials from the environment to fashion implements, in this case by sharpening pieces of stone. Possessing a brain about half the size of a modern human's, Homo habilis took the inaugural step along the technological path that has led to our advanced societies today. It was once thought that tool-making, along with language, was a defining feature that separated humans from all other animals. We now recognize that these boundaries are considerably more fluid than we previously assumed. We can observe animals using rudimentary tools. Chimpanzees, for example, will insert sticks into termite mounds to retrieve and consume the insects. However, it would be unreasonable to suggest that a simple stick is functionally the same as a Boeing 747. As with many traits that distinguish humans, the critical factor is not the existence of a difference, but the immense degree of it. Clearly, the capacity to transform environmental materials into tools is an essential prerequisite for the rise of a technological society. But when we start thinking about life on exoplanets, an intriguing question emerges. Here on Earth, the widespread availability of different kinds of stone gave our ancestors the means to create progressively more sophisticated tools. The same holds true for metals with low melting points, which are plentiful on or near our planet's surface. Without them, we might still be in a Stone Age. However, the easy access to materials suitable for tool-making is not guaranteed to be a universal characteristic of every exoplanet. Imagine a water world, a topic we will delve into in Chapter 8, where rocks and metals could be incredibly scarce. On such a planet, the emergence of what we would recognize as a technological civilization would be challenging, to say the least. Therefore, we should focus not just on the presence of life on other worlds, but also on the availability of resources from which alien life could fashion tools and, eventually, build a technological civilization. This brings us to Chapter 4, The Rules of the Game, or How Every Living System Ought to Work. It's a strange paradox that while defining life itself is exceedingly difficult, perhaps even impossible, outlining the properties that life on other planets must have is a far more manageable task. The reason for this is our solid understanding of how life, at least life as we know it, evolves and interacts with its environment. As we will see, the fundamental principles that govern life on Earth should apply to most other life forms as well, not just those based on carbon. This allows us to formulate the governing rules for any hypothetical life form anywhere in the galaxy, provided we can first grasp what those rules are here at home. With this in mind, and acknowledging that the origin of life on Earth is our only known example, we will begin by examining what we understand about life's development on our own planet. Afterward, we will try to envision how similar processes might unfold under the exotic conditions found on distant exoplanets. To comprehend how life on our world became what it is today, we must find answers to two fundamental questions, which will require us to draw upon a broad range of scientific disciplines. The first question is, how did something living arise from components that were undeniably non-living? This is often referred to as the problem of the origin of life. The second question follows from the first. Once living entities appeared, how did the incredible diversity and complexity of life that we observe today come into being? The next question brings us closer to our conversation about hypothetical life on exoplanets. Fortunately, we have a relatively strong grasp of how this process played out on our own world. Our contemporary understanding of life's progression is founded on the theory of natural selection, or Darwinian evolution, which you might remember from our previous discussion regarding NASA's definition of life. Before we examine the origin of life in detail, I must emphasize a critical point. Living systems on Earth today are extraordinarily complex, representing the culmination of billions of years of evolution. The very first life form on our planet, which we can call the universal common ancestor, was nothing like the organisms you see now. It would have been exceedingly primitive, likely possessing only a small fraction of the characteristics found in modern cells, as all the intricate features of contemporary life were acquired later through natural selection. In its earliest days, our planet was a molten sphere hurtling through space, lacking any distinct atmosphere, oceans, or, of course, any trace of life. As the young Earth traveled in its orbit around the Sun, it was relentlessly struck by cosmic debris. These very collisions generated enough heat to maintain its surface in a liquid rock state, which leads us to the fundamental question we wish to explore. How did Earth transition from this chaotic environment to one harboring at least a single living organism? We operate on the assumption that most Earth-like exoplanets, which are small and rocky, began under very similar circumstances. Consequently, our logic concerning the genesis of life on those worlds is guided by Earth's own history. We believe that gas giants such as Jupiter or Saturn formed through a different process, where hydrogen and helium rapidly gathered around a comparatively small solid core. We can debate later whether this implies that life on such planets might have originated differently than it did on Earth. However, we suspect that the internal cellular structures of any organism inhabiting a gas giant would diverge significantly from those of life here. For instance, some of these structures might be specifically adapted to regulate buoyancy. So, after emerging from its initial molten state, the first thing that occurred was Earth's cooling, causing its outer layer to harden into a rocky crust. Water, sourced partly from the planet's interior and partly delivered as ice by comets and asteroids, then filled the ocean basins, preparing the environment for life's debut. Certain geological discoveries, like zircon crystals that contain water, suggest liquid water was already abundant on Earth as far back as 4.2 billion years ago. Paleontological evidence indicates that life emerged shortly after the planet's intense bombardment by large asteroids ceased, which was no later than 3.8 billion years ago. This means that an observer on our planet 3.8 billion years ago would have witnessed oceans filled with cyanobacteria, which are dense blue-green algae. Essentially, life arose on Earth with remarkable speed, almost as soon as conditions permitted its existence. This observation brings forth a fascinating possibility. During the great bombardment of early Earth, there were probably quiet intervals, perhaps lasting millions of years, without major asteroid impacts. If life had developed during one of these calm periods, it would have been completely wiped out by the next catastrophic collision. A celestial object the size of the state of Georgia, for example, would have delivered enough energy to boil away Earth's oceans and transform its atmosphere into scorching steam for 1,000 years. A cataclysm no primitive life could endure. As far as we can determine, this type of scenario could have repeated itself multiple times in our planet's early history. This suggests our microbial ancestors were likely not the first life forms, but rather the first to survive and evolve following the last planet-sterilizing cosmic event. The initial step toward the origin of life required the formation of complex molecules built around carbon atoms. It was once believed that creating the intricate carbon chains observed in living systems was an exceedingly challenging task. In fact, until the middle of the 20th century, most scientists steered clear of this field of research, as the prevailing attitude suggested the topic was too complex and better suited for philosophy than for mainstream science. The scientific study of life's origin gained significant momentum from a single experiment performed in 1952 in the basement of the University of Chicago's chemistry building. Nobel laureate Harold Urey and his graduate student at the time, Stanley Miller, set out to replicate the conditions they imagined existed on the primordial Earth. Their apparatus was quite straightforward: a flask of water to act as the ocean, a heat source to stand in for the sun's energy, an electrical discharge to simulate lightning, and a gas mixture of water vapor, methane, hydrogen, and ammonia, which they believed mimicked the planet's early atmosphere. After setting up the experiment, they activated the heat and the electrical sparks and let it run for several weeks. At the conclusion of this period, the water had transformed into a murky reddish-brown liquid. Upon analysis, this mixture was found to contain molecules of amino acids. To give you some context here, proteins are one of the most crucial types of molecules in living systems, as they are responsible for controlling chemical reactions in all known organisms on Earth. Proteins themselves are constructed from amino acids, so you can imagine a protein molecule as a chain where every single link is an amino acid. Miller and Urey effectively showed how the fundamental components of living systems could emerge through natural processes, using materials that were undeniably non-living, yet widely believed to be plentiful on the nascent Earth. This discovery had a massive effect on the study of life's origins, primarily because it shifted the entire problem out of the domain of philosophy and placed it squarely within the realm of scientific inquiry. In the wave of research that followed their work, scientists managed to create nearly all the vital molecules found in organisms, including sections of DNA and even complex proteins. Remarkably, it doesn't seem to matter that Miller and Urey's initial assumptions about the primordial atmosphere's makeup were probably wrong. Subsequent experiments using varied atmospheric blends and different energy sources have produced broadly comparable outcomes, with the quantities of molecules changing based on the specific inputs. Moreover, we have discovered complex organic molecules, amino acids among them, embedded in meteorites, floating in interstellar gas clouds, and even within the debris disks around stars where new planets are born. It turns out that, against all prior expectations, the basic molecular ingredients for life are quite ordinary in the cosmos. They are essentially everywhere. With this realization, the central puzzle of life's origin transformed into a new question. How did these basic building blocks manage to assemble themselves into something we would unmistakably call alive? Numerous theories have been proposed to account for this step, though none has managed to win universal consensus. At a minimum, drawing from Earth's own history, we can state one conclusion with certainty. Whatever the mechanism was that transformed inanimate matter into a living state, it must have happened extraordinarily fast. The primordial soup theories, which arose in the wake of the Miller-Urey experiment, posited that the atmospheric reactions they had demonstrated would have led to downpours of organic molecules. These rains would have gradually converted the planet's oceans into a rich, dense organic broth. According to calculations, this transformation would have taken only a few 100,000 years, a mere blink of an eye on a geological scale. Theorists then proposed that, given enough time, random collisions between molecules in this soup would inevitably give rise to a chemical structure capable of gathering materials from its surroundings and making copies of itself. The universal common ancestor. This concept gained such immense popularity that the Smithsonian Institution even commissioned a film in which the famous television chef Julia Child was depicted stirring up a batch of primordial soup right in her own studio kitchen. From this main idea, several different scenarios sprouted, each exploring a unique pathway to the first common ancestor. Charles Darwin, for example, once mused that life could have started in a warm little pond. Building on his thought, some researchers contended that coastal pools, filled with organic rich water at high tide and then concentrated as the water evaporated, would create the perfect conditions for the random molecular assembly that formed the first living entity. Other competing theories swiftly followed, each outlining a different set of conditions that could have facilitated the jump from basic components to self-replicating cells. One idea suggested that the electric charges on the surfaces of clay deposits might have served as catalysts, sparking the initial chemical reactions essential for life. Another group of theorists imagined that every bubble of sea foam, or, in a related version, each tiny fat droplet in the soup, acted as an independent chemical test tube, containing its own distinct combination of molecules. A different scenario still proposes that life first arose within a rocky crevice near a deep-sea hydrothermal vent, a model that conveniently bypasses the need for an initial cell membrane, as the rock cavity itself would have served that protective function. All of these models for the origin of life can be seen as different flavors of what is known as the frozen accident theory. The central premise is that random arrangements of molecules were constantly forming until, by a sheer stroke of luck, one of them happened to be capable of self-replication. As soon as that occurred, the machinery of life was set in motion, and the process of natural selection could begin. The specific combination of molecules that kicked off this entire chain of events became frozen in place, leaving all other potential competitors and late-arriving alternatives in the dust. You could go through your entire existence surrounded by frozen accidents, and never even be aware of it. Just glance at your computer keyboard and observe the QWERTY arrangement of letters in the top row. This specific layout was created back in the 19th century as a clever way to keep the keys of mechanical typewriters from jamming. It essentially became a frozen accident. Although our keyboards today are electronic and have no mechanical parts to jam, we still use the original layout because changing it now would be far too inconvenient. By that same logic, if these origin of life theories are accurate, the very first cell that successfully managed to reproduce became the template for all subsequent life. This wasn't because it represented the best possible biological solution, but simply because it happened to be the first one to succeed. We could spend more time examining other frozen accident theories, but you have likely already grasped the fundamental concept. The Miller-Urey experiment unleashed a flood of speculation and hypotheses about how life began. As researchers learned more about the chemical underpinnings of life, two principal theoretical frameworks emerged and came to dominate the discussion. We will refer to these as the RNA world and metabolism first. Modern cells, it turns out, employ a rather distinctive process to power the chemical reactions that are necessary to keep them alive. These vital processes depend on specialized molecules known as enzymes, and within terrestrial life forms, these enzymes are a type of protein. This fundamental connection is precisely why the publication of the Miller-Urey experiment's findings caused such a revolutionary stir, as it demonstrated the spontaneous formation of amino acids, the building blocks of those very proteins. Inside a cell, the instructions for building proteins from amino acid chains are stored within the intricate DNA molecule. Another set of complex molecules, RNA, is responsible for carrying these instructions to the protein-building machinery. The problem, however, is that proteins are required to read the DNA code in the first place. This presents us with a classic paradox. You cannot make proteins without decoding DNA, but you cannot decode DNA without already having proteins. A potential answer to this puzzle emerged in the early 1980s, when researchers discovered that specific RNA molecules, called ribozymes, could also function as enzymes. This finding gave rise to the RNA world hypothesis, which proposes that a proto-RNA molecule appeared by chance and served a dual role in the first life forms. The central premise is that once this molecule existed, a primitive cell could harness it for survival and replication, becoming the ancestor of all subsequent life, with its complexity arising from billions of years of natural selection. An entirely different perspective, which we can label metabolism first, dismisses the notion of a frozen accident altogether. This theory posits that the earliest living system, or protocell, lacked both DNA and RNA. It suggests that this protocell sustained itself through basic chemical reactions catalyzed by small molecules, without any need for complex enzymes. The sophisticated chemistry of the modern cell, in this view, evolved much later through the gradual process of natural selection. To help you grasp this concept, imagine trying to explain America's federal highway system. If you wanted to understand this immensely complex network, you wouldn't start with a current map and try to reverse engineer traffic patterns. A better approach would be to go back to the primitive network of Native American footpaths. You would then trace how these trails became dirt roads for wagons, then roads for early cars, and were eventually paved and serviced, step by step, arriving at the modern system without needing to assume any single improbable event created it all at once. So, which of these two narratives, the RNA world or metabolism first, reflects what truly happened on the young Earth? The truth is, we have not yet determined the answer, and it is conceivable that neither hypothesis is correct. What we can state with confidence about life's origins on our world boils down to two key facts. First, Earth was rich in the fundamental molecular components required for a living system to arise. Second, regardless of the specific process, the assembly of that first living organism happened very quickly. No matter how life began here, it does not dictate how it must originate everywhere else in the galaxy. Even on planets with liquid water oceans, life could arise in dozens, hundreds, or millions of different ways, potentially using unique molecules for genetic information and different proteins to manage its chemistry. As we continue this exploration, it is crucial that you avoid what might be called Earth chauvinism, the biased belief that all life in the cosmos must be similar to our own. Let's examine some ways these differences could manifest. Even familiar carbon-based life existing in liquid water does not have to mirror what you are accustomed to on Earth. For instance, consider proteins, the molecules that serve as enzymes. While a vast number of amino acids, the building blocks of proteins, can be created, life on Earth uses only a small set of 20 or 22. Is this limited selection just another frozen accident in our planet's history? If so, life on other worlds might have proteins built from entirely different amino acids, resulting in a completely distinct biochemistry. On the other hand, if our specific set of amino acids provides a crucial yet undiscovered evolutionary edge, then we might find that all carbon-based life shares a similar genetic foundation. You can ask such questions about nearly any chemical property of terrestrial life. Take the liquid medium itself. Water is abundant throughout the cosmos. But is it an absolute requirement for carbon-based life to thrive? For this, you might turn your attention to a world like Jupiter. It seems that Jupiter is the most arid location in our solar system, effectively a desert on a planetary scale. This is a remarkably fitting comparison, as information from the Galileo space mission reveals that the water vapor content in Jupiter's atmosphere is similar to that of the Sahara. Yet we are aware that rather sophisticated organic molecules like benzene easily form there through chemical processes initiated by the sun's ultraviolet rays. This demonstrates that complex molecules can arise even in environments with very little water, which leads us to ask if a similar process could trigger reactions akin to the Miller-Urey experiment, ultimately giving rise to life. We often assume that life must be water-based, a belief shaped by our terrestrial experience, and the fact that water is an excellent medium for chemical reactions. For molecules to engage with one another, they need the freedom to move and collide, a process far more efficient in a liquid. However, water is by no means the only liquid solvent in the universe. On Saturn's moon Titan, for instance, you can find entire oceans of liquid ethane and methane. While chemical reactions in such frigid conditions would be exceedingly slow, there is no fundamental reason to believe that life everywhere must adhere to the same temporal constraints as it does on Earth. At the opposite extreme of the temperature scale, you can envision planets so intensely hot that they possess oceans of molten magma or lava. The types of molecules familiar to us could never withstand such a furnace, but it is conceivable that other, unknown molecules could. As is often the case when we contemplate life beyond our world, we are left with a greater number of questions than we have answers. The inquiries grow even more intricate when you shift the discussion to life forms that are fundamentally different from ours, specifically those built on atomic chemistry other than carbon. We have a considerable understanding of how the foundational components of carbon-based life either appeared or could theoretically appear. In contrast, the origin and evolution of life founded on other molecular frameworks remain largely unexamined. It isn't a great leap of imagination, though, to picture an alien scientist somewhere whose body is made of silicon compounds, performing its own version of the Miller-Urey experiment to unravel the beginnings of its particular form of existence. To truly consider life that bears no resemblance to what we know, you have to abandon the principles of molecular chemistry entirely, entering a realm where there may be no chemical building blocks whatsoever. In Chapter 16, when we explore the idea of electromagnetic life, we observe that our grasp of electric and magnetic fields is currently far more advanced than our understanding of molecular biochemistry. We have long understood that moving electric charges produce magnetic fields, and that fluctuating magnetic fields induce electric ones. Yet this knowledge could be completely irrelevant for describing the complex living systems that might emerge from electromagnetic forces. Once the matter of life's origin on a specific world is resolved, and a self-replicating unit has been assembled, an entirely new array of mechanisms begins to operate, and you can imagine the pace of life's development accelerating dramatically. We touched upon this subject in the last chapter, while examining NASA's definition of life and presenting Darwin's theory of evolution. Here, we will delve into how this process sculpted life on Earth, offer solid evidence for the theory, and make the case that evolution must be the principal force guiding life's advancement on any exoplanet. The theory itself is built upon two remarkably simple and self-evident facts. First, individuals within any species display a range of characteristics, and these traits can be passed down to subsequent generations, sometimes with random alterations like the mutations seen in Earth's DNA. Second, members of a species must compete with one another for the finite resources available in their shared environment, which makes the whole process quite straightforward. On our planet, it is undeniable that different individuals of the same species possess distinct attributes. Certain rabbits have the ability to run faster than their peers. The beak shapes of some birds enable them to gather food more proficiently, and some rams achieve more frequent mating opportunities. When Darwin formulated his theory of evolution, he was unaware of the underlying reasons for these variations, or the precise method of their inheritance from one generation to the next. Nevertheless, he knew for a fact that individuals were different, and that those differences were heritable. One of the aspects that makes Darwin's book, On the Origin of Species, so enjoyable to read is the painstaking detail with which he explores the nuances of pigeon breeding. You can almost picture him spending hours in a local pub discussing the topic with fellow enthusiasts. And Darwin did, in fact, breed pigeons himself. The fundamental premise of his theory is that specific genes provide an organism with traits that enhance its probability of surviving long enough to have offspring. Consequently, these particular genes have a greater chance of being transmitted to the next generation. In the vocabulary of paleontologists, we describe these genes as being selected, and with time, they can become prevalent throughout a population. If this selection process repeats itself enough, entirely new species can arise, which connects directly to the title of Darwin's book, as he was, in essence, describing the origin of species through the inheritance of genes. Although Charles Darwin did not coin the phrase survival of the fittest himself, it later became a popular way to summarize the evolutionary process. The critical insight is that the idea of being the fittest or most adapted is always defined by the specific environment in which an organism exists. For instance, in an environment teeming with predators, the genes that enable a rabbit to run faster are highly likely to be passed on to future generations. Conversely, for a creature living where sustenance is limited, different characteristics, like a highly developed olfactory sense, could prove far more crucial for survival. This illustrates that there is no single, universal standard for evolutionary fitness. It is entirely relative to the specific traits that confer an advantage within a particular environment. This gradual, incremental aspect of evolutionary change highlights another critical concept. When you visualize how an organism adapts to its surroundings, you must envision a step-by-step progression where every single stage offers a distinct evolutionary benefit. For this reason, it is illogical to propose that a species like a pig would suddenly benefit from having wings. Instead, you must imagine a plausible, incremental pathway toward developing wings, where each successive modification better equips the organism for its environment. For instance, the evolutionary steps toward wings might begin as small protrusions on a pig's body that initially serve to regulate heat, then evolve to permit gliding, and ultimately develop into fully functional wings. The necessity of justifying each phase in a species' development will be essential when we explore potential evolutionary trajectories under the alien conditions of exoplanets. Before we wrap up our review of the evidence that substantiates the theory of evolution, we need to tackle one final question: the velocity at which the evolutionary process unfolds. On this topic, there are two contrasting viewpoints. The first theory, known as gradualism, posits that significant evolutionary shifts are the result of a slow accumulation of minor, incremental changes. The opposing theory, called punctuated equilibrium, argues that most species experience long stretches of stability with virtually no change, followed by brief, intense periods of rapid transformation. Since the emergence and development of species are driven by alterations in DNA molecules, you can visualize how each of these theories could manifest. A mutation that affects a solitary gene, and by extension a single chemical reaction, typically leads to only slight modifications in the organism. Yet, as we now understand, certain DNA regions function not as protein blueprints but as master switches for entire groups of genes. A mutation within these regulatory areas could initiate a cascade of profound changes, which aligns perfectly with the predictions made by the theory of punctuated equilibrium. As is common in such debates, the most accurate answer to the question of whether life on Earth evolved gradually or in sudden bursts is likely both. Whether this same answer applies to life on exoplanets will hinge on the particular mechanisms those life forms use to transmit traits across generations. While numerous arguments support the theory of evolution, I will be concise and concentrate on two of the most significant: the paleontological record and the findings from DNA sequencing. Among all fossil types, the most striking are certainly the skeletal imprints and other petrified remnants of animals that vanished long ago, which enable us to assemble a comprehensive narrative of life's historical development. Every extinct species we have unearthed so far represents another distinct twig on the intricate tree of life. Other kinds of fossils, like plant fragments and, more recently, the remains of single-celled organisms in ancient rock formations, have also been discovered, which has helped us, as I noted earlier, to approximate how rapidly life arose on the primitive Earth. Since DNA carries the complete blueprint of the organism it belongs to, our ability to decipher the sequence of its codes provides an alternative method for reconstructing the history of life on our planet. The foundational idea here is that the more significant the genetic differences between two organisms, the further back in time their shared ancestor must have existed. By calculating the rate of mutation, often called the molecular clock, you can use this genetic data to build another evolutionary tree that charts the progression of life on Earth. From my viewpoint, the single most persuasive piece of evidence for Darwin's theory is the remarkable correspondence between the evolutionary tree derived from fossil studies and the one constructed using DNA sequencing data. This consistency is so strong that I believe Darwinian evolution should be ranked among the fundamental principles that govern the universe, right alongside phenomena like gravity. Wherever a mechanism exists for traits to be passed from one generation to the next, and for those traits to be altered, natural selection will invariably emerge. When you consider life based on chemical processes, whether carbon-based or otherwise, the environment will invariably present factors that can induce mutations or similar genetic changes, with temperature, ultraviolet light, and chemical reactions being primary examples. Consequently, within any population, individuals will continuously appear who are better suited to their environment than their peers, which is all that is needed to set the mechanism of natural selection in motion. This leads to the conclusion that when we speculate about life on exoplanets, beginning with the theory of evolution is an entirely rational approach. It is vital to stress one final point. While natural selection will always be the fundamental law guiding the development of life on exoplanets, the kinds of living systems it fosters will differ enormously from one environment to another. For example, for life existing in the upper atmosphere of a gas giant, the capacity to control one's buoyancy could be a tremendous advantage, enabling an organism to travel between atmospheric layers to find food. On a planet in synchronous rotation, which we will explore in a later chapter, the ability to endure the violent winds that scour the surface might give an evolutionary edge to low-slung, streamlined creatures. In the sections that follow, we'll explore the conditions present on a variety of exoplanets to see how they might steer the course of natural selection for our hypothetical life forms. It is, however, worth admitting that it is far more captivating to consider circumstances where the principles of natural selection might not hold true at all. And I'd like to present a couple of such scenarios for your consideration. Natural selection fundamentally relies on the competition for resources among separate individuals. But what if a life form on an exoplanet existed not as distinct entities, but as a single interconnected whole? Here on Earth, the largest known living thing is the Armillaria ostoyae fungus in Oregon, a solitary organism stretching more than 3 kilometers across, which makes it easy to envision a similar organism blanketing an entire world. On a planet dominated by a single life form, there would be no individuals to compete against one another. So would this mean natural selection couldn't take place? This is a sophisticated problem that demands a thorough examination. The fungus I mentioned is composed of cells that divide as it expands, a process susceptible to the environmental pressures we discussed earlier. In an organism spanning a whole planet, the mechanics of cell growth and division would function just as they do in smaller beings. Consequently, if mutations arose in the cells of this colossal creature, you would likely find that cells in different regions had adapted uniquely to their local environments. In essence, natural selection would operate on different sections of a single organism, rather than on separate members of a species. The only way to dismiss this idea is to imagine that a planet-sized organism materialized spontaneously in its final form. A possibility so remote that we can confidently set it aside. Another scenario to consider involves a perfect planet. The primary engine of natural selection on our world is the relentless transformation of its surface, driven by geological processes deep within its core, forcing Earth's organisms into a perpetual state of adaptation. But what if a planet were different? Imagine an exoplanet where conditions remained utterly stable for billions of years, allowing life to evolve to a perfect equilibrium with its surroundings, at which point all evolutionary pressure would cease. This doesn't imply that mutations would halt. They would continue to occur at their normal frequency. It would simply mean that no mutation could possibly improve life on this perfect planet. As a result, new mutations would eventually be filtered out, and life would settle into a condition of complete stagnation. We occasionally observe something similar on Earth, where each mutation creates what the German geneticist Richard Goldschmidt termed hopeful monsters, most of which have mutations that don't impact their survival and thus vanish within a few generations. It isn't a great leap to imagine this situation extending to the point where these hopeful monsters no longer appear at all, which is what life on a perfect planet would resemble, if such a world actually exists. The purpose of these two examples is to serve as a caution. As we venture out to look for life in the galaxy, we will have to meticulously and repeatedly question almost every rule we think we know, and resist the urge to jump to conclusions. This is simply the way the universe is built, and our only option is to accept this reality and take pleasure in it. Chapter 5. In Search of Life. Is anyone there? Mars is, without a doubt, the first place on our list of celestial bodies where finding evidence of living organisms seems relatively achievable. Over the last 50 years, a veritable armada of spacecraft has been dispatched to the Red Planet, with landers touching down in numerous locations. Even as I write this, the Curiosity rover is making its way up a mountainside near the Martian equator that has captured the interest of geologists. By this point, you might expect we would possess a definitive answer to the question of whether life exists on Mars, or ever did in its past. But that is not the reality. Ever since 1976, when the Viking landers, two of humanity's pioneering spacecraft, alighted on the Martian surface. The scientific world has been locked in a slow-moving debate over the evidence, or lack thereof, that these probes uncovered. The importance of this debate is difficult to overstate. Unless we can invent a technology like Star Trek's warp drive in the near future, it's highly improbable that we will ever investigate another planet with the same level of detail as we have Mars. Yet, if after half a century of intense scrutiny we are still unable to say for certain if there is or ever was life on our planetary neighbor, what hope do we have of resolving a similar question about a planet situated light years from our own? The quest for life on Mars can be accurately described as a chronicle of disappointments. Time and again, we have encountered phenomena that appeared to be unambiguous indicators of life, only to later discover that they could be explained by mundane chemical reactions. We keep gathering clues and hints, but as of yet, not a single one has provided a conclusive answer. It has been nothing but a series of letdowns. In the year 1976, two separate Viking landers executed successful touchdowns at different sites on the surface of Mars. Each probe was equipped with instruments to carry out 4 distinct experiments intended to find signs of life. The first of these was a molecular analysis using a technique called gas chromatography mass spectrometry. A second, the gas exchange experiment, involved mixing Martian soil with water and nutrients to monitor for any potential biological activity. A third, the pyrolysis experiment, tested for photosynthesis by exposing soil to carbon-based gases before heating it. The fourth experiment, which I will delve into shortly, was designed to detect organic compounds. For the first 3 experiments, the conclusions were quite clear-cut. They revealed no indications of biological activity whatsoever, and in fact, failed to find any organic molecules at all. It's crucial to remember that these tests were all engineered with the underlying premise that Martian life would operate on a metabolism similar to that on Earth, an assumption that, as we covered in Chapter 3, may or may not be valid. Moreover, the experiments were only set up to screen samples from the most superficial layers of Martian soil, reaching no more than about 2.5 centimeters deep. The experiment designed to find organic compounds, however, garnered immense attention, and the debates surrounding its results have spanned decades. The procedure was as follows. A sample of surface soil was sealed in a chamber, into which a solution of water and nutrients was introduced. These nutrient molecules were specially prepared with a significant amount of carbon-14, a heavier isotope, in place of the usual carbon-12. While carbon-14 shares most chemical properties with ordinary carbon-12, its radioactivity makes it exceptionally easy to track within any given sample. The logic behind this test was elegantly simple. If the Martian soil contained microbes, these organisms would consume the nutrients and, in the process, release radioactive carbon dioxide gas. The presence of this gas could then be identified within the chamber's atmosphere. And to everyone's surprise, both Viking landers did indeed register the release of gas containing this labeled carbon dioxide. Regrettably, the initial euphoria that followed the publication of these findings did not last long. When the nutrient solution was added to the chamber a second and then a third time, no further traces of the radioactive carbon dioxide were detected. Scientists reasoned that if microbes were responsible for the initial gas release, their population should have grown, leading to an even greater emission of gas with each subsequent feeding. On the other hand, if the carbon dioxide was the product of a non-biological chemical process, the reactive agents would have been used up, preventing the reaction from happening again. Since the latter is precisely what the data showed, the conclusion at the time, and the one that largely holds today, was that the Viking missions found no conclusive proof of life on Mars. However, this is not where our story concludes. Since 1976, a small but very passionate contingent of scientists has maintained that a proper interpretation of the Viking data actually confirms the existence of microscopic life on the red planet. To give you an idea of how persistent this debate is, at a major NASA conference on extraterrestrial life in 2016, the question and answer period following one presentation was almost entirely consumed by a fervent and at times quite contentious discussion about the Viking mission's findings. But the hope for confirming Martian life isn't built exclusively on the Viking results. As far back as 1971, the Mariner spacecraft, while orbiting Mars, transmitted images of the planet's surface that stunned the world because they so closely resembled Earth's own river systems. In the years since, a multitude of orbital missions have provided undeniable proof that liquid water did indeed once flow across the Martian surface. During its early history, the planet's northern hemisphere even held a vast ocean, which existed around the same time that life was first emerging on Earth, lending widespread credibility to the notion that life may have once thrived there. Even if that ancient life perished when Mars lost its oceans and atmosphere, proponents of this idea have long argued that we might still discover its fossilized remnants. There is, however, one particular characteristic of Mars that makes scientists doubt whether any traces of past life, in the form of organic molecules, could have possibly survived to this day. Because Mars has no magnetic field, its surface is perpetually bombarded by intense solar radiation, which creates high concentrations of hydrogen peroxide, an extremely potent disinfectant that effectively sterilizes the surface and breaks down any organic matter. And yet, in 2018, the Curiosity rover managed to discover organic molecules embedded in rocks that had formed back when the red planet was still covered in water. Although these molecules are unlikely to be the byproducts of any currently living organisms, their discovery offers us hope that molecules once belonging to living systems could indeed have been preserved. So, could it be that Mars is completely lifeless today? We have only ever probed the very uppermost layer of its soil, never penetrating more than a few inches down, which raises the question of whether something vital might be concealed at greater depths. As the Curiosity rover navigated through Martian canyons, the Mars Reconnaissance Orbiter was capturing images from high above that revealed dark streaks appearing on the planet's surface, which seemed to change with the seasons. These features were thought to be caused by spontaneous eruptions of briny water from beneath the surface. While some scientists now propose that shifting sand, not water, could be the cause, the possibility of subsurface water remains open. Furthermore, in 2018, analysis of data from the Mars Express orbiter led researchers to suggest that a lake of liquid water might exist directly under the planet's north pole. If liquid water truly does exist beneath the surface of Mars, it naturally leads us to wonder if that water could also harbor microscopic life, presenting another tantalizing possibility for us to consider. Beyond this, we also have the detection of methane on Mars. The methane molecule itself is quite basic, consisting of a single carbon atom attached to 4 hydrogen atoms. Here on Earth, we know methane as the primary component of natural gas, a substance often associated with biological activity and used for everything from heating homes to generating power. You can find trace amounts of methane right here in our own atmosphere, at a concentration of about 1,800 parts per billion, which is roughly 0.18%. The vast majority of this gas, around 95%, originates from microbial life, though non-biological sources can also produce it. For example, methane can be released when magma in volcanic craters comes into contact with groundwater, or through a much slower process involving the transformation of iron oxide, or rust, into different minerals. Using ground-based telescopes and techniques involving spectroscopy, astronomers first confirmed the presence of methane in the Martian atmosphere back in 2003. The quantity was minimal, just 10 parts per billion by volume, a fraction of what we find on Earth. But its existence was undeniable. A decade later, in late 2013 and early 2014, the Curiosity rover witnessed a baffling phenomenon. Atmospheric methane levels abruptly surged to 10 times their normal amount before plummeting back down just a couple of months later, an event scientists named the methane spike. What could have triggered this peculiar event? One possibility is that a bubble of methane, created through standard non-biological chemical reactions, was simply released into the atmosphere. However, it's just as plausible that the spike was caused by a sudden bloom in the population of microbes living beneath the surface. Consequently, while the detection of methane is an intriguing clue, it unfortunately serves as another tantalizing hint rather than definitive proof of life inside Mars, leaving us with yet another disappointment. Let me tell you a remarkable story about ALH 84001. It begins in the Allen Hills, a desolate cluster of hills in Antarctica located roughly 200 kilometers south of the primary U.S. base at McMurdo Sound. If you were to visit, your view would be dominated by vast, endless ice fields and glaciers inching their way towards the low mountains. The common reaction to such a place is to wonder why anyone would ever choose to come here, but the answer is surprisingly straightforward. People come for the meteorites. To understand why, you need to know about the unique process at play here. When a meteorite lands on a glacier in the Allen Hills, it becomes embedded deep within the ice, and the glacier's slow movement carries the rock along with it. As the ice flows upward against the gentle slopes of the hills, powerful winds strip away the surface layers in a process known as ablation, exposing the meteorite. In effect, the entire ice field functions like a massive conveyor belt, collecting fallen meteorites and bringing them directly to the surface for discovery. In 1984, a team of scientists on snowmobiles came across one such meteorite on the glacier's surface. It wasn't much to look at, being about the size of a grapefruit and weighing around 1.8 kilograms, with a dark outer crust from burning through Earth's atmosphere. It was catalogued as ALH 84001, signifying the first meteorite found in the Allen Hills that year. Following this, the rock was boxed up, sent to a laboratory, and remained there, largely forgotten, for almost 10 years. When researchers finally took it out for analysis in the mid-1990s, they realized they had stumbled upon an extraordinary find. The chemical composition of gas bubbles trapped inside the rock was a perfect match for the atmosphere of Mars, proving it was a Martian meteorite. While this discovery was significant, it wasn't unprecedented. By that time, science had already identified over 100 other rocks that had been blasted off Mars by asteroid impacts and later landed on our planet. The truly compelling aspect of ALH 84001 was its incredible age. Radiometric dating revealed the rock itself had solidified approximately 4 billion years ago, during a period when Mars was known to have abundant liquid water. Its journey began around 17 million years ago, when an impact launched it into space, where it orbited the Sun for eons before finally falling in Antarctica, about 13,000 years ago. This means ALH 84001 is a silent witness from the very epoch that life might have arisen on Mars, a time when our planetary neighbor bore a striking resemblance to Earth. Everything changed in 1996 when a team of NASA scientists, headed by astronomer David McKay, made a spectacular claim. They announced that their examination of ALH 84001 led them to conclude it held the fossilized remnants of ancient Martian organisms. This extraordinary assertion was supported by 4 key pieces of evidence: the detection of organic molecules known as polycyclic aromatic hydrocarbons, or PAHs, mineral structures within the rock that physically looked like fossilized Earth microbes, mineral groupings that mirrored those created by terrestrial bacteria, and finally, chains of magnetite crystals resembling those produced by certain microbes on our own world. It's hard to overstate the shock waves this news sent through both the scientific community and the general public. The announcement garnered so much attention that it was even acknowledged by the U.S. President at the time, Bill Clinton, at the White House. This high-profile interest is thought to have been a key factor in establishing NASA's astrobiology program, an initiative that thrives to this day. Inevitably, as time went on, McKay's team encountered significant pushback from other scientists. For instance, critics argued that the presence of PAH molecules was not compelling evidence, as these organic compounds are ubiquitous in the cosmos, having been detected in comets and even in the lifeless void of interstellar space. Regarding the structures that looked like fossils, skeptics noted that certain purely non-biological mineral formations on Earth can also mimic the shape of cells. Furthermore, the supposed biological structures were about 100 times smaller than any known terrestrial cell, leading to the hypothesis that they might be a new class of life called nanobacteria, a concept that is theoretically possible but has never been observed. Lastly, it was proposed that the specific mineral combinations offered as evidence could have been inadvertently created during the laboratory preparation of the samples for viewing under an electron microscope, rather than being original features of the rock. For a while, the most compelling evidence for the Martian origin of these fossils was the presence of magnetite chains. On Earth, bacteria use these chains like an internal compass, aligning with the planet's magnetic field to navigate murky waters. This finding was significant because early Mars might have had a magnetic field, making such a feature evolutionarily advantageous for any life that may have existed there. However, scientists later showed that magnetite crystals, much like those in the ALH 84001 meteorite, could form through entirely non-biological means, particularly during the intense heat and pressure of entering Earth's atmosphere. This left us with ambiguous evidence yet again, where the structures could be either Martian fossils or the product of natural non-living processes. Ultimately, we still cannot definitively say if life exists, or ever did, on a planet we have explored so extensively, which naturally makes you wonder how we could possibly search for it on distant, unreachable exoplanets. Back in the early 19th century, the French philosopher Auguste Comte, who founded the discipline he termed social physics, now known as sociology, made a list of things he believed science would never uncover. High on this list was determining the chemical composition of stars. His logic was straightforward. Since the only known method for chemical analysis required a physical sample in a lab, and we could never place a piece of a star on a lab bench, their makeup would forever remain a mystery. It's easy to guess what Comte would have thought about exoplanets. Being unreachable, their chemical nature would be similarly unknowable. Yet this entire line of reasoning was overturned in 1859 when two German scientists, Gustav Kirchhoff and Robert Bunsen, met in a laboratory in Heidelberg. Kirchhoff is famous among physics students for his rules on electrical circuits, while Bunsen is credited with inventing the essential laboratory burner that bears his name. Together, they performed a series of experiments where they passed the light from a heated, pure substance through a glass prism, breaking it down into its constituent colors. Instead of the continuous rainbow they anticipated, they found that every chemical element produced a distinct and unique set of colors, a pattern exclusive to it alone. We refer to this combination of colors today as an emission spectrum, and there's a related phenomenon called an absorption spectrum, linked to the absorption of photons at specific energy levels. The entire field dedicated to studying these patterns is called spectroscopy, and you are already familiar with its practical effects. For instance, you have likely seen the yellowish glow of some street lights, which are sodium lamps used in foggy conditions because their specific light color penetrates haze more effectively. Since every element has a unique color signature, observing this optical fingerprint allows us to identify its presence in any light source with absolute certainty. A critical feature of spectroscopic analysis is its indifference to distance. Whether the light source is a few centimeters away or billions of light years across the cosmos, the fingerprint remains embedded in the light beam forever. It's also amusing to note that while a modern spectroscope with a built-in computer can cost thousands of dollars, Kirchhoff and Bunsen constructed their first one using a couple of old eyeglass lenses and, incredibly, a few cigar boxes. It wasn't until the early 20th century that the scientists developing the new field of quantum mechanics could finally explain how atoms generate these unique spectra. They used a simplified atomic model, which showed that unlike planets around the sun, an atom's electrons are confined to specific distances from the nucleus in what are called permitted orbits, or orbitals. Each orbit corresponds to a distinct energy level. Consequently, when an electron jumps from one orbit to another, the atom either emits or absorbs a precise amount of radiation matching the energy difference between the two levels. Radiation is emitted when an electron moves closer to the nucleus, and absorbed when it moves farther away. Because the atoms of different elements have unique sets of orbitals, each element emits and absorbs its own characteristic set of colors, creating its spectral signature. This principle isn't limited to just atoms. Any system with distinct energy levels, including complex molecules, can produce a characteristic fingerprint through processes like vibrating, rotating, or altering their geometric shape. This makes spectroscopy an ideal tool in our search for life on distant exoplanets. All we need to do is detect the spectral signatures of biological molecules in the light from these planets to find definitive proof that life exists there. Consider our own planet as an example. The existence of life on Earth has a profound effect on the chemical makeup of its atmosphere. In fact, among the hundreds of known atmospheric gases, only a small fraction have not been influenced in some way by the activity of living organisms. Consider helium, which constitutes about 1% of our atmosphere. Its origin dates back to the Big Bang. Argon is even rarer here on Earth, produced from the radioactive decay of potassium deep within the planet's core. In contrast, all the other gases in the atmosphere are generated, consumed, or modified by biological activities. The very oxygen you breathe is a byproduct of photosynthesis, a process where plants use sunlight to transform water and carbon dioxide into carbohydrates. Solar ultraviolet radiation splits the molecular oxygen from plants into individual atoms, which then combine with other oxygen molecules to create ozone. Meanwhile, processes like respiration and decomposition release carbon dioxide, effectively reversing photosynthesis. Some gases, like hydrogen sulfide, are produced by blue-green algae, and, as I've noted, certain bacteria emit methane. Earth's atmosphere is rich with these indicators of life, which we refer to as chemical markers or biosignatures. You might assume that using spectroscopic methods to find these chemicals in the atmospheres of exoplanets would be a direct way to confirm the presence of life. However, this approach is fraught with three considerable difficulties. The first obstacle is that exoplanets themselves are exceptionally faint sources of light, visible to us only because they reflect the light of their host stars. Detecting this faint, reflected light across the vast distances that separate us from even the closest stars is an extraordinarily challenging task. Despite this, astronomers have recently succeeded in analyzing the radiation from numerous exoplanets by employing highly sensitive detectors and sophisticated observation techniques. The most effective method involves measuring the light from the parent star while the planet is concealed behind it, and then measuring their combined light when the exoplanet passes in front. By subtracting the first reading from the second, we can isolate the spectral characteristics of the exoplanet's own light. The second problem lies in pinpointing the markers of specific molecules within an exoplanet's spectrum. While every element and molecule possesses a distinct light signature, the unique part of the spectrum that serves as a biomarker often represents a minuscule fraction of the planet's total spectral output. This requires us to gather an immense amount of light from the exoplanet, a task that typically demands the use of enormous telescopes. The third problem is substantially more complex than the first two. How can you determine, with certainty, which biomarkers genuinely signal the existence of life? We've established that most gases in Earth's atmosphere are produced or modified by living things, so it would seem logical to search for these same gases around distant worlds. The reality, however, is not so simple, because nearly every molecule we consider a biomarker can also be formed through non-biological means. Let's look at oxygen. Ultraviolet light from a star can split atmospheric water molecules, freeing up oxygen atoms that can then form molecular oxygen. While photosynthesis is the source of most oxygen on Earth, it isn't the only source. The same issue applies to methane, which, as I've mentioned, can be produced in many ways that have nothing to do with biology. Hydrogen sulfide, known for its rotten egg smell, is produced by certain bacteria on Earth, but is also expelled during volcanic events. This list could be extended, but the central point is clear. Almost every molecule you might propose as a potential biosignature for an exoplanet has a non-biological formation mechanism in addition to a biological one. Some researchers suggest that the key is to look for combinations of molecules produced by life. For instance, consider oxygen and methane together. Methane is unstable in Earth's oxygen-rich atmosphere, yet its continuous biological production ensures its presence. If all life on Earth were to cease, methane would vanish from the atmosphere in a matter of decades. Oxygen would persist for several millennia before being absorbed through the oxidation of minerals. Therefore, the simultaneous detection of both oxygen and methane could be a powerful biomarker. Even though each gas on its own would tell you very little, finding such biosignatures on exoplanets is, naturally, a far more intricate task than simply looking for familiar gases. This field of research is rapidly evolving and is a subject of constant debate among scientists. The interim conclusion from these discussions is that we cannot confidently claim to have found life on an exoplanet based on the spectral lines of individual atoms or molecules. The most promising path forward appears to be the search for combinations of gases that are biologically produced. So, to summarize the next step in our understanding, we know that life on almost any exoplanet must operate by natural selection, but we now also see just how formidable the challenge is to find irrefutable proof that such life actually exists. For now, let's put that specific problem aside and instead concentrate on how the laws of natural selection might function under the varied conditions of the numerous exoplanets we are aware of. This shift in focus leads us directly to what can be described as the study of imaginary life, or speculative biology. In the upcoming chapters, I will present a collection of brief, imaginative essays detailing how a human, outfitted with the necessary protection and highly sensitive instruments, would likely perceive the environmental conditions upon arriving on these distinct exoplanets. I have opted for this particular method of introducing new worlds for a very simple reason. As has been stressed repeatedly, life on Earth is the only form of life known to us, which makes humans the only species whose reactions to alien environments we can predict with any degree of success. With that framework established, our speculative journey can now commence. I invite you to direct your imagination toward our first destination, a world I have designated Iceheim, a kingdom defined entirely by ice.